Hey, good evening, folks. I was in another meeting, so I had turned on another link. I changed the channel link back to this one. Welcome to today's class. So, welcome to today's class. Today, we will learn about MOSFET device and what are the various fundamentals associated with MOSFET device. So, before that, hope everybody is ready for the class. Any questions?
Yes, sir.
From last 2 days? Let me know. Premateja, you are in this class?
Yes, sir.
Were you able to set up the students' windows for them?
What, sir? Sir,
Okay. I hear very nice music. Over it is, can you mute yourself? Oh, Premateja, yourself. Huh? Are you still in the bus by any chance?
Yes, sir.
Okay, continue. So I just wanted to know, can you set up the simulation environment on lab machines for the students?
Sir. No, sir, not it.
Okay, set it up and let me know. We will go through some of the things in class, how to simulate the questions, okay? Or you can take a class for all of them. Say this Saturday. Why don't you take a simulation class for them? Right? Can you introduce them to the tool, the PDK, the model files? This Saturday, can you do that? 2 hours anyways you have, you can go through some of the simulations. Sorry?
Yes, sir.
Okay, great. So this Saturday class, Premateja is going to be your faculty. She is going to take you through what is the simulation tools, what are the model files, what are the various simulations.
Yes, sir. Saturday,
There's too much of noise from your side. So we will speak to you when you're little better off. Oh, yes. Okay, let us have a look at the course. Another 6 people to join. Shall we start or wait for them?
You can start now. Director Javed, you can start it now. No problem. They will be all, most of them will be traveling, so you can start it. No problem.
Okay, so let's go through. I will turn off the video. Let the video be on. We will discuss. So today we will talk about MOSFET. What is a MOSFET? 12th standard physics, you would have heard and read about this. A MOSFET is designed or developed on a P substrate, which is a P-type substrate, single crystal silicon wafer, which gives the physical support and is basically the carrier of the device. In the P substrate, you will add 2 heavily doped N regions along the width of the device, right? So these 2 heavily doped N substrate on a P form a PN junction. So this is one diode. So if you really want to simply create a diode, you already have a PN junction available. Now with this, connecting these 2 N-type heavily doped N regions is going to be an insulator thin layer of silicon oxide, which insulates the gate, which is the conductive material on top of the silicon oxide, and the channel below, or the substrate below in which the channel will form. On top of the silicon oxide is going to be a thin layer of polysilicon, which is heavily doped and it is conductive. So this will be the structure of a transistor, and this forms the polysilicon forms the third junction with the N device, and here is also another diode will form. So you basically have two PN junctions present in the circuit, and this PN junction forms the channel transistor. What is a transistor? Basically, it says it's a transfer resistor. So you are going to transfer the resistance either from a low resistance to high resistance to high resistance, or high resistance to low resistance. So this is called the transfer of resistance is going to happen through. So you have the three terminals decided. So the N plus heavily doped region on either side are called the source and the drain, and the heavily doped conductive polysilicon which is there on top is called the gate. Now this is what you look from the side view, and from the top view it looks as follows. So the black region here is called the P substrate. The green shaded is the end heavily doped N region, and the red region is the polysilicon. Here is where you will understand what is the length and width of the device. The length of the device is along the vertical between the two N doped region is what is called the length of the device. Why is this the length? This is taken in such a way that when you apply an electric field between the source and the drain, it is the field which is going to come in this region. Either the field will be bottom to top or top to bottom. So this determines the length of the field. So based on this, the device length is named in this direction. And in the horizontal direction is going to be the width of the device. So W is the width of the device. So this is how do we define the MOSFET? We define the MOSFET geometry as W by L, which is width and the length. There are many other factors dependent on this transistor. First thing is the silicon dioxide thickness, which is called the oxide thickness, is directly present. This oxide thickness is directly contributed to the amount of capacitance present between these two devices. So this basically is CSD, or your C gate to source. So between the gate and the source, or the gate and the drain, you will get the capacitance, which is epsilon Tox by A. So what is the thickness of the oxide, and the total area of the gate will give you the capacitance. So the W by L, CGS, Tox, and what is the voltage that is applied at each of these terminal is brought out. So this is represented in many ways. The symbolic representation of an NMOS that we will consistently use in this course is as follows, where the three terminals are defined. So source will have an arrow present with it. The drain is on the opposite side, and the gate is the control device. This is going to be your NMOS. Next is going to be your PMOS device. Same gate control G. The PMOS device is source on the top side. We will symbolically write it. Drain will be written symbolically below. Why is the arrow going inwards? It is just a nomenclature or a notation that is used. There are two other nomenclatures that are used using the bubbles. So the NMOS device comes without a bubble, which shows its non-inverting characteristic based upon the gate input, and other one is the bubble which comes on the gate, which shows that it is inverting. Now, if you look at this bubble nature and the direction of the arrows, there is a current apparently going outwards. So the way you see is current flows from source to drain or drain to source. So this is the direction of the current. In this case, this will be the direction of the current. The other way, the electron flow will be in the opposite direction. Electron flow will be the opposite direction. So the net positive charge will flow in the opposite direction of electron flow. So this is going to be the symbolism that we will follow in this course. Consistently, I will be using the arrow-based devices in this course. So somebody had unmuted. Any question? I think I'm seeing a new student today, Pawan. Any question? No question. In that case, we will proceed. So what is the current flow? How does it get created? So the current flow gets created when there is a field applied gate, source and drain. So when there is a voltage applied, voltage V1, voltage V2, and the entire ground or the bulk is maintained at lowest potential for an NMOS. This lowest potential here considered to be the ground. We are discussing an NMOS device. That is because you have got 10 plus here. So depending upon what is the voltage that is applied at the source and drain, a field is generated. Now the field will start from the device with a higher potential to lower potential. Let us assume in this condition, V1 is greater than V2. So the field is generated from left to right. This is your electric field. Once this field is generated, now there is enough electron deposition on each side to ensure that there is charge flow for you. So a channel keeps forming like this, and at one particular voltage difference where V1 minus V2, this difference is greater than or is equal to the threshold voltage, a channel or a path for electron conduction is generated. This is called channel for current flow or electron flow, right? So electron flow happens in the opposite direction of current flow. So net positive charge will flow through. So this is the thing. So whenever you have a voltage difference, V1 minus V2, here you will get this threshold. Now, when does the current actually start flowing? When a potential is applied here. What is the potential applied here? This is your gate potential. Now, what is the minimum gate potential that is needed? The minimum gate potential that is needed is equal to what is the junction voltage greater. So the PN junction needs to be turned on for current flow. So what is the threshold value of the PN junction? That is given as VTH. So current starts flowing when the gate to source voltage VGS equal to VG minus VS is equal to or greater than the threshold voltage. This threshold voltage is defined for the PN junction over here. So current will start flowing only when there is present here. Now, why does the current start flowing? For that, you need to understand something called inversion layer. Right? What is inversion layer? Inversion layer is a thin layer in the p-type silicon. Right? What is it? It is a thin layer in the p-type silicon. Where is the p-type silicon? This is the p-type silicon, right? P substrate. Very thin layer in the p-type silicon, where majority of the carriers are free electrons. Thin layer in p substrate. Second condition, majority carriers are free electrons. Right? Only when there are free electrons will there be current flow. So the formation of a inversion layer is important. So where does this inversion layer happen? Inversion layer happens between the N plus of the source to the N plus in the drain. That is this region that is highlighted by red. Right? Now, once this layer happens, when you apply a small potential voltage to the gate, you will have something called as a conducting channel. What is it called? It's a conducting channel. When does this appear? It appears when a small voltage is applied to the gate. After the field is created. Before the field is created, you will not get this. So important is source and the drain have to be applied with the potential, and a small voltage then should be created in the gate. This will create a conducting channel. Right? So the condition for the conducting channel should be as the VGS should be greater than or equal to the threshold voltage for any conductor. Understood? Now, with this analysis, let us come to an understanding what are all the various conditions that we have for this to operate. Right? Now, with this condition, with threshold voltage, now we will try and build a few case studies. Let us build the case study slowly. So the way we build is, now we have, so first condition for conducting channel, we have a condition that says VGS should be greater than or equal to VT. This is one of the case. But let us start with case 0, or say case 1, which says case 1, which is what happens in the when you apply the voltage where your VGS is between 0 and VT. Right? In this case, let us define VGS is gate to source voltage. Let us define the other variable VT is called threshold voltage. Threshold voltage. Okay, so threshold voltage for typical devices lies between 0.35 to 0.5 volt, right? This is applicable all the way up to 65 or even say 45 nanometer. And for less than 45 nanometer of length, this value can be anywhere between 0.2 to 0.35, right? So giving you a heads up, your textbook will use this value, whereas the industry will typically use this value. So all through this course, we will align ourselves to this, right? And when we are doing a project or when we are completing the course, we will introduce you the industry value for less than 45 nanometer. But in this course, since we do not have access to a PDK, which is less than 45 nanometer, all our discussions will be limited to up to 45 nanometer. So we will use 0.35 up to 0.5 volt, right? So this is the value that we'll go through. Now, question would be, first question that I will ask is, does the channel exist here? Right? For a conducting channel, you need VGS to be greater than VT. So the first thing is there is no channel. No channel here. And this is said to be cutoff mode. Okay, cutoff mode, we will use this in analog design, and in digital design, this mode is commonly called as off or logic 0 or low. Okay, this is the common case. Next, we will do is case 2. Okay, for case 2, let me ask who is here. Let me start with the first person, Geetika. Geetika, can you please unmute and say what will be the second case? Geetika?
Yes, sir.
Yeah, what would be the second case that we can check? First case is your VGS voltage is between 0 and VT. What could be the second case? This is all 12th standard physics, right? We are only having a look at it now. Okay. Who is next? Arvind.
Yes, sir.
What will be the next case in this case, Arvind?
VGS is greater than or equal to VTH.
VGS is greater than or equal to VTH. Very nice. So what would that be? So the way we will write is, your VGS is greater than 0. Another thing is, VGS is greater than or equal to VT. Right? So just to make your life simple, I will draw something like this. So this is your 0. This is VT. So first case is, this is VGS 1. VGS is between 0 and VT. Second case is VGS is 2. It is greater than 0. It is greater than or equal to VT. So that would be this region. We will see what else will come there. So understood? Who was the first person I asked? Geetika. Did you understood now? What is the
Yes,
next
sir.
case?
Yeah, yeah.
It has to be intuitive. Okay. Next. Please go through this here. Who was there? You've got Dhanashri, Hemashri, Sri Chandana. So next question will be to one of these three. Be ready. So this is VGS. Another thing is condition is V source to drain or drain to source is 0. Now in this condition, what is the value? In this condition is you'll have to see is a channel being formed? Yes, channel is formed. Channel is formed, right? But one condition is there is no electric field, right? We said there needs to be an electric field between the source and the drain. But since the source and drain have no potential, there is no potential difference. So for this reason, no current. Okay, no current. So what does this happen? So in this case, channel is formed, but no current flow. Right? Next case. Hemashri. What is case 3? So here is VDS 0. This is the clue. So VGS 1 is between 0 and VT. VGS 2 is greater than 0 and greater than or equal to VT. But in both cases, VDS is 0. What is the third case? Case 3. Hemashri not responding. Dhanashri? Dhanashri not responding. Sai Chandana?
Yes, sir. VDS less than VT.
VDS less than VT. Very good. So VDS will be here. Right? Let's see if that is the correct answer. So first thing is your VGS is not changing. So VGS is greater than 0. VGS is greater than or equal to VT. Next, your VST or VDS is greater than 0, but VDS is less than your VT. So, Sai Chandana, your answer was partially correct, right? What is this? Your VDS will be less than this voltage, because what we said, for current to flow, a small gate voltage has to be applied after the channel is formed. So that the condition will be, remember, this is the most important question in understanding device operation. So it will be VGS minus VT. So VDS is in between VGS and VT. So VGS minus VT should be greater than VDS. So that would be the case. Now, what is this case? In this particular case, you have transistor in what it is called as linear mode, meaning the current has started flowing. So how does the device look like? So this will be your channel. N plus P sub. This will be your gate. So you will have the channel which is formed. Right? So what happens? There will be a current flowing from IDS. So there is a current flowing in the channel, right? And this is called linear mode. Depending on what on the voltage that you apply, that small amount of current will flow. This is also called triode mode. Why triode? Because you have got two PN junctions with 3 terminals. So this is a diode structure. You will have 3 terminals, so it is called triode mode. Now what is the current? IDS proportional to VDS. Okay. IDS is now proportional to VDS, and the current is now working. What is this mode called as? This mode is called as voltage controlled resistance. Voltage controlled resistance. Why is that? When you have IDS is equal to VDS by channel resistance R. So the amount of voltage that flows present divided by what is the resistance here. The resistance which is controlled by voltage will give the total current to flow. So you have a voltage controlled resistance in this mode. So you can also add in the linear mode, you can make the transistor work as a resistor, or also called active resistor. Remember. So this question is a common interview question. It will appear as a gate exam concept. Okay, this will be commonly used in all the gate topics and others. Understood? Very, very important. Understand this concept. When a transistor can be made to work as a resistor, when the VGS is greater than VT and the VDS is between VGS minus VT and 0. In that condition, you can make it as work as a resistor, right? Next. What is the next condition that we have? What is the next condition? Whom can I ask now? Okay, before I ask, let me ask Premateja itself. Premateja? In this third case, where you have a transistor who is in this condition, where the VGS is greater than 0, okay, and VGS is greater than is equal to VT, and the VGS is between 0 and VGS minus VT. We have defined a condition in the previous diagram saying it can work as a voltage control resistance, right? So we will call that as resistance as RDS. RDS is equal to VDS by IDS. Now, I want to know two things. If I draw a waveform, I want to draw, say we said voltage control resistance, right? So now this is the VDS, voltage. Now I am controlling the resistance to find out what is going to be the ID current output. So what will be the graph that you will see? What are all the controlling elements here? So this is the linear mode. So what will be the relationship between VDS and ID? Very, very important question. I'll give you a clue. Now RDS is equal to VDS by IDS, right? I will say RDS now is function K prime times VGS minus VT by IDS. Now this should give you a clue. We said that VDS has to be less than VGS minus VT. So I'm saying instead of VDS less than, I'm saying some factor K times VGS minus VT. What is the relationship that I will get here? What is it? Okay, the benefit of out of time, it is going to be a linear relationship. When I said, see, the clue was here, linear. Linear means straight line. You will have this characteristic. Right? You will have this. Now, why have I drawn so many things? If you go back, I said something interesting here. A small voltage is applied at the gate. Depending upon what is the gate voltage applied, you will see the current flowing. That will be the conductive channel. So this would be for various voltage of gate to source supply, VGS1, VGS2, VGS3, VGS4, etc. Different VGS values, you will get different, meaning as you increase the VGS supply, the current through the device will go up. Right? So this is the gate to source. So this is VGS. Right? This is VGS. So what we will do? Another is this is D. Drain to source, VDS. So VDS is needed to create a channel. I'm repeating again. VDS is needed to create a channel. VGS is needed for current flow of current. So as your VGS goes up, your flow of current will also go up. Now, for example, if your VDS is at this voltage, for VDS1 keeping constant, as you increase the VGS, you will get different values of VGS, different values of current. Right? Likewise, you add a different value of VDS, you will get a different value of current, ID. So this is the way it works, right? So this is called transfer characteristic, or you could say the RDS is a function of VGS minus VT while VDS is constant, right? So this is something that is important to follow. It is a voltage controlled resistor, and here. So what is the control? How do you remember this? I will give you a simple way of remembering. Is if you have a water tank, big water tank filled with water. that water tank has an outlet. Right? That water tank has an outlet. Okay, this outlet is now controlled by a valve. You will be surprised to see that this valve in some places is called a gate valve. Right? This also has a nice story. Gate valve terminology comes from the gate in dams or reservoirs used to block water, block the flow of water. Right? When this gate is turned on or the gate is lifted, water will flow. Same thing here. If this knob is turned, opened, then this black region will slowly open up. The black will slowly open up, allow the current to flow, or the water will flow. Now, what is this? When can a channel be created? When there is an electric field present. So the electric field means there is water in the tank. Water in tank is equivalent of the electric field in transistor. Remember that. If there is no water in the tank, water cannot flow itself. So this is a very common gate question. Remember this analogy. If they say there is water in the tank, means field is present. If there is no water in the tank, means field is absent. Whatever you do, the gate valve, how much ever you open and close, water cannot flow. So unless a channel is created, right? Unless a channel is created, that is, unless the water is there in the tank, nothing can flow. So always remember. Next, how much you open the gate wall, that much water flow will come out here. Even if there is full tank water, you open it very less, you will only get less water flow. If you open it fully, you will get more water flow. So this is directly related to current. Right? So this will be your current flow. This is your VGS. This is your VDS. Always remember. Right? This is the easiest analogy. So depending upon how much you put at the gate, you will get that much value. Clear? Now we will see what is the next flow. Next flow is, what is the next flow? We have this inequality, right? Now let us fill up that inequality. What is that? Let's come back here. Till now we said VGS, VDS is less than VGS minus VT. Now what will happen if VDS is equal to VGS minus VT? So that is going to be our fourth case. Case 4. Case 4 is your VGS is greater than or equal to VT. Your VDS is equal to VGS minus VT. So this is the new condition now. Come again. Quick reminder again to know where the two. Top side is VGS, bottom side is VDS. Here you have VT. Right? So it says VGS is greater than or equal to VT. So this is the area where VGS minus VT can be. So this is your area anywhere here. Now what is VDS? VDS is equal to VGS minus VT. So this is the VT voltage, VGS minus VT, assuming it is here, right? So this is your VDS minus VGS minus VT. So what happens in this condition? In this condition, the channel that you have, the channel, if you look at it, how was the channel before? The channel had a deep, broad area here. Now this channel, as you apply the VGS minus VT here, it becomes very narrow. So how does it become? It becomes like this. So this is what your channel will be. Right? Now what happens here? Channel is big. This is the direction of current flow. This is I ds. So this is the direction of the current flow. And this stage, it is just slowly come off. This, what is called as the VGS minus VT, the channel is slowly getting narrow and narrow. It will be a point signal here. And this extremely narrow region is called pinch off region, or pinch off happens in the channel. So at pinch off, what happens? As the pinch off appears, there is a limit to the amount of current that can flow. So IDS will stop. IDS will stop increasing. It will remain the same irrespective of what is the VDS supply there onwards. So there cannot be further increase. IDS will remain same no matter how much VDS is increased. Right? That means there is a limit. What is this? There is the limit to the outwards flow, and that limit is defined by the diameter of the pipe. Right? No matter how much water you tank in increase, it is limited by the diameter of the pipe. That is the only diameter which will allow flow. Rate of flow of water equivalent to rate of flow of current. So that is called, so you will have a limitation there. No matter how much VDS increases, your IDS will remain the same. So it pinch off. So here, what is the condition? The channel just reaches the drain. Right? We were speaking about an inversion layer. This inversion layer just becomes 0. Right? And this stage is what we call as pinch off. Clear? So as your VDS is equal to VGS minus VT, you will hit pinch off. So this is another gate question or interview question. What is the nature of the channel when VGS is greater than VT and VDS is equal to VGS minus VT? Remember, when VDS is equal to VGS minus VT, it gets pinched off. Right? So that should be the first understanding. Next, the next case that comes is, so let's, who's next in the list? Farah Naz. Are you there, Farah?
Yes, sir.
So Farah, what is the next stage, Farah? What is the next case?
VDS is greater than VGS minus VT.
Correct. So case 5. Case 5, no change in VGS status. VDS is greater than VGS minus VT. So here, so the question is, now that channel is pinched off, as you continue to increase, will the pinch off continue? No, because now you are limited by the diameter of the pipe. So that is fixed. Whatever said and done, that is fixed. But how will the channel look here? The channel will look as follows. I am drawing it in the same page just to show you the difference. How will the channel look? How will the channel look? The channel will look almost the same, but slightly less pinched off. Or rather, I'll slightly little moved away. Slightly more than pinch off would be available here, right? There will be a finite space. There is some amount of finite space available. So in this condition, what will happen? As VDS increases, your ID will remain the same. Or you would say ID will saturate. Or you could say it remains unchanged. So in this case, this ID is approximately constant. It's not directly related to. It is approximately a constant value. K times VDS. So it will be a constant value where K prime can be, or K will be equal to 1 also in many cases. So this is called saturation. Current saturation happens in this condition. So now we will go back to this curve. VDS and ID. We said what is the nature of the current? So as the VDS is small, how is the current behaving? So I will draw VDS on the x-axis and ID on the y-axis. So what happens when VDS is small? When VDS is small, that is less than VT, you have a high current increase, right? After the VDS increases, what happens? It will start. What did we see here? As the VDS is small, current rise is large. But as the VDS increases, it starts stabilizing, right? It starts stabilizing slowly. But as the VDS increases beyond a certain point, it does not respond in any way. So it is stable, right? Now this is the nature. It is here that we will define the modes of operation, wherein here ID is directly proportional to small VDS. Here increasing the VDS increasing the VDS increases the resistance also, or reduces the conductivity. This is called channel resistance. Right? The conductivity increases, and beyond a certain point, that is this region, ID is constant to VDS. So what is the condition for all of this? The common condition is VGS is greater than or equal to VT. So this is the VDS versus ID dependence or transfer function. Now, in general, we will now define the three modes that are associated with this condition. First one is cutoff. Where is cutoff? When VGS is less than VT. So it is this zero stage. Next is triode, where VGS minus VT is greater than 0. So you will be in the linear region. So this is your linear region. Third, it is in the saturation region, where no matter how much you increase your VDS, your ID is saturated. So these are the three distinct operating modes. Distinct modes of operation. Right? These 5 cases that we have seen is extremely important for the rest of this course, because everything else depends upon how these are present. Right? Now this graph is designed for NMOS devices. The same thing happens for PMOS. What is that? Let's come again. Let us see what is happening. NMOS device. Drain, source, gate. This is your VGS. This one has a threshold VT, VGS minus VT. Finally, the channel dependence is on the VDS. Now, what happens when you do the same in PMOS? This is your source, this is your drain, gate. What is this? VSG. And there is VT and there is VSD. Right? So first thing what happens? Same condition. When your VSD, right? VDS inverted SD. So you will have a cutoff region on the 0. When your, this would be your cutoff region with no current. After that, when you have ID is responsible to small VDS, VSD. So this is small VSD. Okay, this is called your triode region, or it is called your linear region. After that would be your saturation region. What happens in the saturation region? Your VSD saturates with ID, and ID is directly dependent on VGS minus VT. In this case, VSG minus VT. So since VGS is equal to minus VGS, or the direction inversion polarity changes, the direction in which this is present also changes. So this is the work. Right? This is important with respect to the IV characteristics that we see. VDS versus ID characteristic that we discussed. So any questions here? So we will summarize. So what is the, let us summarize today's class. First is cutoff region. Now, whose chance is it now? Chanakya, you're there? Harshita, Vani Harshita? Or Lasya Priya?
Yes.
Who's this, Vani or Lasya? Who just said yes? Okay, somebody said yes and doesn't want to say no. So in the cutoff mode, we will summarize. Conditions for the cutoff mode are VGS is less than or equal to, VGS is greater than or equal to 0 and less than or equal to VT. IDS is 0. Next, linear mode. Linear mode, your VGS is greater than or equal to VT and your VDS is greater than 0, but it is less than VGS minus VT. This VGS minus VT is also called as VD saturation or VD sat, right? So VGS is VGS minus VT. Third one is your saturation mode. So in saturation mode, again, the same condition follows. VGS is greater than or equal to VT and VDS is greater than VGS minus VT. So these are the three conditions in which it works. So what are the channel? For the channel, what are the conditions? What are the channel conditions here? Channel condition is this is cutoff, right? And here it is linear or it is triode. Then the boundary condition here is between linear and triode and saturation. You first get the pinch off. After channel pinch off, then you have the saturation. Right? So this is what we will be using almost every time in everywhere. Right? These are the conditions that we are working on. How do you summarize this in a circuit way? So, okay, we did not write in the saturation mode, right? Your current IDS is directly proportional to VDS, and here IDS is constant after VDS is greater than VGS minus VT. So in those two conditions, your transistor, okay, your 3-terminal transistor will work as a linear resistor. So this is the linear mode. Next, the same transistor right? Will work as a, what we said, IDS is constant. So it will work as constant current source. Right? So this fundamental understanding is needed for designing all the other circuits later. When we say circuit is in saturation, the assumption is it is now behaving as a constant current source at all points of time. So fixed amount of current is going to flow through it. So that is the two very important conditions. Now in this current source also you have two variants. You have the PMOS. So in the PMOS, the source is connected to VDD and this is there. So you'll have a current source going outwards with one supply on the VDD. Similar on the NMOS, the source is connected to the ground. So the constant current IDS now flows to the ground from here. So this is very important for understanding what is the saturation that goes through. Right? Now we will start the next class with linear mode and constant current source. What is the current equations and what are the conditions of current flow in those cases? Right? Any questions? Any questions from the people? If no questions, it is time to take our customary photograph. Please turn on your cameras. Now let me see how many people are at home, how many are outside. So Dhanashri is outside on two-wheeler, listening on mobile phone. Prema Teja doesn't know has she already reached home or still in the bus? Oh, it's raining for you, Dhanashri. Background you're covering with a nice umbrella. Geetika is laughing her heart out. She doesn't want to speak, but she's definitely laughing her out. Look at her expression. Okay. Karthika has been silent today. What happened, Karthik?
Nothing, sir. Nothing, sir. I'm just listening. That's it.
Only listening, no interaction.
Stealth mode sometimes.
Stealth mode. It's a good one. Let me see. There is. Aha, my snipping tool is here. Able to see this share? Okay. Hopefully all please look into the camera and give a nice smile. Ah, that's right. Gotcha. Okay. I had shared the, remember? I had shared the lecture notes. Did you get to see the lecture notes for the 3 classes before?